All right, so this is for Chem 102. We're going to go through sections 12.3 and 12.4. So we're going to start talking about solids in this video, and the first thing we want to look at is melting point. So solids moving to a liquid. This graph is showing the melting point temperatures at which those solids break free of that structured form to get that liquid form. I want you to notice an interesting pattern. I want you to think about why these three, why do they go up instead of continue along the line here, or maybe like this one kind of is straight across. Like, why do these three go up? So pause for a moment, think about it. I'll give you the answer in the next slide. If you look here, it's because of the intermolecular forces. So we have these three, you might have noticed, are hydrogen bonding compared to these are dipole-dipole. So the stronger your intermolecular force, the higher your melting point, because the particles are held closer together and tighter together, they're going to be harder to take apart from that whole structure. So we have, if you look at just a couple that have maybe a similar mass, like these two have a similar mass. Dispersion versus dispersion plus dipole-dipole, look at the difference in the melting point there. So we increase our melting point by almost 100. Just by adding the extra dipole-dipole, even if the masses are about the same. Notice also the really big ones. These are the ion-ion interactive forces. So if it's an ionic compound, it doesn't have partial positive and partial negative charges like the other intermolecular forces. We've got full charges here. And then if we look at two that have the same intermolecular forces but different masses, we can see a difference in their melting points as well. Mass is going to increase the strength of the dispersion forces because the more mass or the more electrons you have to move around, the more likely they are to be uneven, and the more likely you are to have that polarizability for dispersion. So larger masses give you stronger dispersion forces, and stronger dispersion forces ups your overall attraction and therefore upping your melting points. We talked about vapor pressures of liquids, but some solids can also have vapor pressure. So solids that immediately turn into gases, like the main ingredient of mothballs, which you smell, like they're a solid, but you can get that vapor, you smell them really quickly. We have iodine, which is a solid, but will vaporize pretty easily. And then you have carbon dioxide, which is a solid at low temperatures. And then in room temperature, it will vaporize immediately or sublimate. Two different types of solids. We're going to hone in on the crystalline solids, but there are amorphous solids. You're familiar with an amorphous solid. Glass is an amorphous solid. It's more like a solid, but then it kind of has like a liquid structure. It's kind of not quite as structured, but still retains properties of a solid. There are a bunch of different types of glasses, but these are the main types of, or three types of glass on the different things that they're made of. And then we use them for different things because sometimes we need absorbing ultraviolet light. Like I want my windows to absorb ultraviolet light so that the ultraviolet light doesn't come in to my vehicle or into my house, right? But we want it to also transmit visible light at the same time so I can see. So there's different glasses they use for different properties. A Pyrex glass, which we use in the lab and in cookware, it has low thermal expansion. So that means that it's not going to crack or break if you do a quick temperature change for it, which is important in cooking and in lab work. We're going to be focusing on crystalline solids. And so basically a crystalline solid is made up of these little unit cells repeating over and over again to make a big crystal. So we break down that big crystal into one kind of repeating piece. That repeating piece is called a unit cell. There are lots of different types of unit cells. If you get into inorganic chemistry, you'll work with all of these. We're going to be talking about a simple cubic cell. It's a cube, so each side, ABC, is the same length, and then each angle is 90 degrees. So we're only going to be focusing on the simple cubic cell for this class. Coordination number is the number of atoms surrounding an atom in a crystal lattice. So if we look at an atom, how many are surrounding it? And we got to think about it in terms of, okay, well, there's also other ones on the other side. So I could draw in like more here. And so if I'm this atom, I could count 1, 2, 3, 4, 5, 6, 7, 8. And then another 9, 10, like you could count more. I don't actually think these are neighboring. So neighboring would be this one, this one, this one, and this one. This one back here, and then this one kind of in the front up here. Um, so I'll give you information about neighboring cells or coordination numbers depending on the type of unit cell that it is. We're going to be using, um, so an array, I guess, is a multiple unit cells together. And again, a simple cubic cell is what we're going to be talking about in this section. 3 types of these simple cubic cells. You have primitive, which is just the most basic, body-centered, which we have an atom in the middle of the box there, and then face-centered, which is we have an atom that kind of cuts the plane of each of the faces of the cell. So body center, there's an atom in the center of the body of the cube, and face centered, there are atoms in the center of the faces of the cube. A body-centered cubic cell has a coordination number of 8. So if you're the center, you have 1, 2, 3, 4, 5, 6, 7, 8 things touching you. And then this one also has 8 things touching it because it's the center of its other cell, right? And we can keep thinking about these repeating as we go. We kind of layer within the depressions and stack based on that for body-centered cubic. And so see, you can see here, here's a unit cell, body-centered cubic. Here's a body-centered cubic. Here's a body-centered cubic. We can kind of just keep going over one and get our body-centered cubics, and we can imagine that it would just keep going from there. Face-centered cubic, the coordination number is 12. This one's kind of hard to see, so we pick our middle guy here in purple. These are actually, this is the same, I couldn't splice these on top of each other, but this is the same one, and then that should make this one purple. So my purple one is actually the same here. So I can make these a different color. I don't think you can see it. No, it's not purple, it's pink. So these two are the same. They don't look the same. Let me fix it. So these two are the same, and then these 4 are actually the same. So I'll kind of try to make those darker green. Here, I can make them darker green. These are the same, and we kind of think about putting them on top of each other. Unfortunately, I couldn't take my 2 images and do that. So who is touching the purple ones? The purple one in the middle here is being touched by 1, 2, 3, 4 on this side. 1, 1, 2, 3, 4 along its own axis, and then 1, 2, 3, 4 on this side. So that gives us 12. You can also just memorize face-centered cubic is 12. Most of the cell's atoms are actually shared by the neighboring cells. So if you are on a corner, you're shared by 8 different unit cells because we stack them on top of each other. If you're on an edge, you're shared by 4 different cells, and if you're on a face, you're shared by 2. So if we want to count how many actual atoms, complete atoms we have in each unit cell, we have to take what kind it is and how many other cells it's being shared by and divided by that number. So for the basic, the primitive cubic cell, we have 8 atoms in the corners, right? So just 8, there's nothing in the center. And then we're sharing it, every corner is shared by 8. So corners are always divided by 8. And so that's one total atom inside of a simple primitive cubic cell. The body-centered cubic has 1 hole in the middle, so we just add that one, that counts as 1, and then we have 8 corners. So 8 corners divided by 8. Corners are always divided by 8. So 8 in the corners divided by 8 is 1, and then we have just a whole one in the middle, so 2 total atoms in a body-centered cubic. Now face-centered cubic is a little more complicated because, well, I guess not so much, but we have 8 corners, so corners are divided by 8, so that's 1, and we have 6 faces. And for faces, we're only sharing them, we cut them in half, so we're sharing them only with 2 different unit cells. So faces are divided by 2. Corners are divided by 8. So we have 6 atoms on the faces. Each side of the cube is 6. There's 6 sides to a cube. So we have 4 atoms total, 1 that adds up the corners, and then 3 for all the 6 faces divided by 2. We have two types of ways we can pack in these atoms into these structures: hexagonal close packed, or HPC. The whole name is hexagonal close packed. Don't just call it hexagonal. So hexagonal closed pack structure. And this is going to be a layer of atoms. So the B layer is in the depressions of the first layer. And then we have another A layer. So A, B, and A. So if you see ABA, that's hexagonal close packed. Cubic close packed is the third one is like different. It looks the same here, but it's actually not directly over the A. So I think the image here might be a little bit off, but I have a simulation for you that will definitely help with this. So if it's ABC repeating, it's cubic close packed. I think C makes cubic close packed. If it's AB, it's hexagonal close packed. If it's got a C in it, it's cubic close packed because there's C's in cubic. So here's another picture of those closest packing. So hexagonal, and you can see that there's like different ways of, this is just everyone is in the grooves of everyone else. This one, the C layer, kind of messes things up because it doesn't go necessarily right in the grooves and doesn't line up with A. So A and C don't have matching. It looks like it here that A and C are matching, but it doesn't actually. So actually it should be maybe just like one here. But if you look here, it's easier to see. A doesn't fit. If it's in the groove of C, it doesn't fit. It doesn't match. I mean, it matches where C is, but it fits in the groove. So we don't have another right underneath the A. Just remember, ABC cubic, C cubic, ABA, AB, hexagonal. And make sure you write closed packing, hexagonal closed packing, and cubic closed packing. That's the whole name of it. Or HCP and CCP. Now, when we're talking about atomic radius, we can actually do a lot of calculations and figure out a lot of cool things about our unit cells. We know that for our cube, each side is the same. And so we're going to represent the side, a length of the side, as A. And then the atomic radius, we'll say R. And atomic radius, again, is half of the diameter of the atom. So for a simple cubic cell, a primitive cubic cell, the A is just two radii put together, right? Because they're all kind of packed in nicely. So just two radii next to each other, so 2R. For a body-centered cubic, we have a little more space because that extra one in the middle is going to give us a little space. So we need to think about the angles of all of this stuff. And you don't need to worry about deriving all of this, but you do want to know this formula here. So we want to know these formulas. This one for simple cubic. This one is for body-centered cubic. And this one is for face-centered cubic. But basically, the A is for the length of the side, and the R is for the radius. And so we can use these formulas to figure out the atomic radius, or the side of the cube if we needed to know that. So here's an example. Gold crystallizes in a cubic close-packed structure, which is face-centered, and has a density of this. What is the atomic radius of a gold atom in angstroms? And for angstroms, checking to see if you have it on your periodic tables. Don't know that you do. I don't think you'll be asked on a test to give angstroms necessarily, but I'll go ahead and give you an angstrom. It's 10 to the negative 10 meters. So an angstrom is 1 times 10 to the negative 10 meters, and that can help you with that. So why don't you try without help first? Okay, so hopefully you tried it a little bit. So here's a kind of a strategy. Basically, what can we do? We know the face-centered cubic is the side is equal to a square root of 8 times the radius. And we know the face-centered cubic is 4 atoms in one unit cell. Remember, for face-centered cubic, it's got 8 corners and 6 faces. So it's 4 atoms total in there. So we're fitting 4 atoms in one cell. And we know density equals mass over volume. So if we can find the volume, we can find the length of a side, because length of a side, if in a cube, side cubed is volume. So we can find the side, we can plug into here, we can get the radius out. So how do we find the volume? We got to plug in the mass because we have the density. So we need to find the mass of the unit cell. Now, if we know there are 4 atoms in one unit cell, and we know the mass of each atom because we know the molar mass, we can figure that out easily. So the mass is going to be 4 atoms in one unit cell. We can cancel out atoms using Avogadro's number. We cancel out moles using molar mass. And so now we know the mass of each unit cell. We take that mass, plug it into density, get volume, and then get the side and plug that in here. That's the plan. So if you want to finish it up, go ahead and try to finish it. And then the next slide will show the answers. All right, so we have our mass. Density is 19.3 given to us. So our volume is going to be this many cubic centimeters. So what's one side? Take the square root of the volume. That's one side. And then we can plug in that one side divided by the square root of 8, and we get our radius. Now radius is in centimeters here, but they ask for angstroms, and so we know that 1 angstrom is 10 to the negative 10 meters, and we know 1 centimeter is 10 to the negative 2 meters, and we can just do a little converting there to get our angstroms. So hopefully that makes sense. If not, if you got lost anywhere, go back to it, try it again, and text me if you need some help. I'm going to go a little bit faster through this section because there's not a lot of new information. So ionic crystals are very similar to what we're talking about. A unit cell of an ionic compound is basically the ions and the cations, but we can actually just think about it as one or the other. And so we can define the unit cell according to the anions or the cations. And so it can be easier for us to try to figure out which one we want to look at for whatever question we're trying to find. And so here's some simple crystal structures. The simple cubic lattice would look like this. This is an example of a face-centered cubic. So you can see the atoms kind of hanging out of the faces. And then this one is also based on a face-centered cubic. But these are really complicated. I'm not asking you to draw any of these. I just want you to know what they look like. And we can actually only look at you can look at the zincs only, so this one is kind of easy to look at the sulfurs. Do you see the face-centered cubic if you just look at the yellow ones? Right? And then for this one, look at the little calciums. That's the gray ones. Can you see the face-centered cubic if you look at the gray ones? So you have to just pick one thing to look at. For this one, we would look at only the chlorides. So here are all the chlorides. It's just your simple one. So kind of ignoring one of the ions will help you figure out what's going on as far as the structure. So how many of each ion are contained within a unit cell of zinc sulfide? And so here's your zinc sulfide here. Can you figure out how many of each ion would be in there? This is kind of hard. So here's our strategy. We got to determine how much each ion is being put in. So the unit cell has 4 zinc ions completely in the cell, but maybe we're not sure how to figure that out. Let's look at the sulfur ions. It's easier to think about the sulfurs. We know the sulfurs are face-centered cubic. And so face-centered cubic means that we're going to have 8 corners divided by 8, and then 6 faces divided by 2. And so our number of sulfurs is going to be 4. And if we look at our just our structure, or not a structure, but a chemical formula, if I have 4 sulfurs, I probably need 4 zincs to balance that out. And that's one way you can think about it. That's oversimplifying it. However, just for you to answer some questions, that would help us figure that out. You can also, this one's like literally looking at the figure and just like counting. The zincs are totally interior, so they are just counting all as one. But you got to make sure the ratio in the compound's empirical formula is matched, right? So if I have 4 of these, I got to have 4 of these. If I have 6 of these, I gotta have 6 of these because it's a 1-to-1 ratio. So I would focus on finding the one that is easier to see, the face center cubic or body center cubic or primitive cubic, and then use the formula to get the other one that maybe is more internal. So here's another example. So the edge length of the sodium chloride unit cell is 564 picometers. Determine the density in gram per cubic centimeter. So try it and then come back. I know these are difficult, but you can do them. So we just got to break it down. So the strategy here is that we can know the number of the ions in a unit cell. There are 4 of each. I think you would have needed to be told the NaCl is simple cubic or primitive cubic. I think that that question is missing that information. So you'd have to be told that to know how many are in each cell. So in a simple cubic, there's 4 because there's 8 corners only, right? And so it would be just the simple, just the simple cubic with the 8 corners. So 1, 2, 3, 4, 5, 6, 7, 8. So there's going to be 4, oh no, hold on, 4 of each. How do I get that? Oh, it must be face center cubic if there's 4, not primitive. Yeah, they didn't tell us anywhere what type it was. So if there's 4 inside of a unit cell, that must have been face center cubic. And again, they would have to tell you that in the question. I wouldn't ask you a question like this and not tell you what it was, because how are you supposed to know how many are in there? So if we know there are 4 of each, we can determine the mass. Same way we did before. So we'll determine the mass using the same kind of formula as this one up here, right? Using the molar mass of the sodium ion or sodium chloride. Oops. Or just the sodium, and then you would also do the chlorine separately. And then you can do AMU to gram with Avogadro's number, but again, I think using molar mass and going from mole to gram and then just thinking about 4 um, 4 ions and then use Avogadro's number to go from ions to moles and then moles to the molar mass is going to be the easier one. In 1 unit cell, the masses of the sodium are going to be that number, and then the mass of the chlorine is going to be that number. And then the length we can turn into centimeters, and we know the length cubed is going to be the volume. So we wanted the density, right? Mass over volume. So we have to add up 4 of these and 4 of these, and then divide it by the volume of that number. So the solution would be the mass of 4 sodiums, 4 chlorides, and the volume of the unit cell is that length cubed, and then we can divide them to get the density. So go back and look at it. I think there's some questions in your homework that'll help, and we'll definitely do some practice in class. And then a couple other things about solids. We have covalent crystals. Covalent can also make crystalline solids. For example, diamond is all carbon, but it's in a very specific orientation. And then graphite is also carbon, but they're in different orientations. So graphite is like in these sheets, and then diamond has this like more rigid 3D structure. The network is held together entirely by covalent bonds, it's not ionic. And then molecular crystals are molecules that are the thing that's holding them together is the intermolecular forces. And hydrogen bonding is an example of that. So how do we get like an ice crystal? It's because of hydrogen bonding. So here, the thing that's holding together the atoms is actually covalent bonds. Here it's ionic bonds. And then up here we've been talking about is covalent or ionic interactions. This is hydrogen bonding for the molecular crystals. It'll be whatever the intermolecular force is. Then you have metallic crystals, and metallic crystals, the electrons are just kind of delocalized all over. We call that sea of electrons. but again, you're not going to really have to focus too much on that. All right, so here's another example. So the metal iridium crystallizes with a face-centered cubic unit cell. Given the length of the edge is 383 picometers, what's the density? So try again. Now they actually do tell you it's face-centered cubic. So see if you can apply what we talked about from the last question. All right, so face-centered is 4 atoms per unit cell. And so we can do our mass to get the total mass of the unit cell. We can get the length in centimeters. So we have 4 atoms in each cell. Here's the mass of a single atom that we calculate. You can also get the mass of the whole unit cell the same way we did in the first question. Then you're going to cube the side of in centimeters, because that's what we're looking for, and then divide it to find the density. So hopefully that wasn't too difficult. Don't let it scare you. Just kind of break it down into pieces. We'll do some examples in class for sure. And so here's a little summary table for crystals and their general properties. You can take a look. And yep, we'll talk about the next section in the next video.